Okay, so this will be all experiments, and the biggest thing about setting up an experiment is random assignment. And then usually between two groups. Between two groups, and you see a vocab word up there, treatment groups. Okay, you would have the two different treatment groups. And we have talked very briefly about, I think maybe on the first day, when we talked about induced variability, when one group wasn't allowed to go to sleep, and the second group was allowed to sleep, and then they all took the same test, and we kind of looked at the differences. That's an experiment, because I'm randomly assigning them, and I'm then saying, you guys are getting this treatment, and you guys are getting this treatment or no treatment at all, and I'm going to see if the treatment causes a difference. Okay? Suppose 50 people were chosen to try out a new diet pill to help increase weight loss. The people are randomly divided, and that's key for you or for us if you're ever asked to describe an experiment. If we don't see the word random, you immediately will lose a point. Okay, you have to randomly assign people to two groups. One is given the pill, while the other is given a placebo, which is essentially a fake pill that does nothing. There are two main ways variability can be introduced into the results. Discuss each. Okay. If the group's average weight loss is different, it may be due to coincidence. Okay, for example, let's say we do that experiment and one group on average loses 10 pounds and the other group on average loses 10.1 pounds. Is that extra tenth of a pound due to the drug, or is it just so happen that by natural variability between, people that might have been placed in, you might have coincidentally placed people in the one group that are more likely to lose weight just because they're heavier to begin with and they have more weight to lose. So that, if it was due to coincidence, that would be called natural variability. We don't ever expect the two groups to lose the exact same amount of weight on average. They're going to be different. The question is, how different do they have to be for us to make the conclusion that it was actually caused by the drug? Does that make sense? And we're going to get a cutoff for that. So is 1/10 of a pound different enough? Probably not. If one group lost 10 pounds and the other group lost 15 pounds, would 5 pounds be enough to convince us? I would think so. Somewhere in there, there's a statistical cutoff that we're going to look at as to what is going to make it significant enough. And the second scenario is that still the average weight loss is different between the groups. And the second option is that it is actually due to the treatment pill and to the drug that the one group took. This would be called induced variability, and both of those vocab words actually came up our first day when we were talking about the different kinds of variability and the different kinds of surveys. Induced means we caused it. Okay, we created an environment that we hypothesized would cause this to happen. Okay, this extra review summarizing practice on the bottom is completely out of place. It's just because I wanted these things on the back side to be all together. So these two examples on the back are really our notes. So go to the back. And I want you guys to get out your calculator. And I'll tell you in a second, once we read this, what we're doing. Actually, Jake, can you read this? Jake Clancy, can you read this for me?
It's left 40 seeds and randomly distribute the seeds to two groups of 20. The seeds in group 1 are given the organic nutrients, and the seeds in group 2 are given the synthetic nutrients. After 3 weeks, each plant grows and plants.
Perfect. So, hopefully I felt that was a pretty clear paragraph to explain what was going was going on here. You've got 40 plants, 40 seeds, 20 are randomly chosen to be treated with organic nutrients, organic fertilizers, I guess we would say, and the other 20 are randomly assigned to receiving synthetic nutrients. And the growth, so this first plant grew 6 inches over the 3 weeks' time, and this plant grew 25 inches, and this plant grew 9 inches, and this plant grew 28 inches. So the growth is then measured. So the instructions here are to enter these lists into our calculator, state the average of each, and then create a box plot or a 5-number summary, box and whisker, or whatever you call that. I don't pick one group. How about you guys do group 1? Everyone insert the data for group 1 and run your statistics. And while you're doing that, I'm going to do it for group 2. Is there anybody who... If you don't remember how to do this, just come right up here, bring your calculator with you, and I will tell you. Don't worry about what I'm doing. I'm doing the second group up on the board. Seriously, if you don't know what you're doing, don't sit there and just hope for the best. Come up and ask me, because if I call on you for the numbers and you then tell me that you had no idea what you were doing, I'm going to be upset that you wasted a few minutes. You have to run your statistics. You hit stat, go over to calc, and it's the first one, variable statistics. You typed everything into list 1, so that's right. And then just go down to calculate. Okay? So we're going to pull the average, and it also asks you to create the box plot, which is the 5-number summary at the end with the min, the max, Q1, Q3, and the median. Okay? All right, let me go with chance. What was the average for that first group that you got?
15.15.
Molly, is that what you had? Okay. So for group 1, 15.15. Right? And I already did the 5-number summary for the synthetic. So I need the 5-number summary for the organic. What was the minimum, Kaylee? 6. What was the next number, Morgan? No. 12. 25 was the max, right? So 6, 12. The next number, Margaret? 15. That's your median, your middle. The next number, Alexis? 18, and someone already gave us the maximum of 25. So these are the organic nutrients. At first glance, Riley, what conclusion would you make? Say it one more time. The organically fed plants are smaller. I would agree. Not only is the entire box plot shifted to the left, but also your median is lower, your minimum is lower, your maximum is lower. It looks pretty convincing. But there's other ways we can spin data, okay? If someone wanted you to think that the organic ones were, not as beneficial for the growth of the plant, they might just do this and be done with it. But statistics can be spun in a lot of different ways, so it's all how people sell it. So that's, generally speaking, something that you should have already known how to do. And so we're comparing the two groups here. But then we're going to take it to the next level into this simulation. So in exercise 4, we have if the average of the first group and the average of the second group are given, and we know what those are, find the observed difference. So the observed difference, and they specify here x2 minus x1. So the second group's average, which is 17.45, minus the first group's average, 15.15. This is the difference in average heights that we actually observe. So 17.45 minus 15.15. What's going on with the lights here? Very weird. So this is our observed difference, 2.3, which means technically that the synthetic group is 2.3, does it say inches or millimeters or anything? I'm going to go with inches. Synthetic group is 2.3 inches taller on average. So can I say done? There you go. If you buy these nutrients, these synthetic ones, your plants will be 2.3 inches taller. No, you can't guarantee that. It's obviously what this study shows. It's likely, maybe. In stats, there's another thing I want to communicate to you. If you're ever asked to explain anything, and what are the chances, or what conclusions can you draw, never give definite. Never say that if you buy synthetic, your plants will be taller than if you buy organic. You don't know that. You don't know if you just got lucky. What if the seeds that happen to end up in this synthetic group were just bigger seeds to begin with? What if from the start they already were the ones that would have grown taller anyway, given no nutrients at all? You don't really ever know anything for certain in statistics. Instead, you're going to use words like likely, or it's very likely, or it's unlikely, or it's very unlikely if you really want to sell it. But you're never going to say it's definite, and this is the way it is. It's likely that this is the way it is. So it seems to be likely that synthetic nutrients are better. Okay, but we haven't run a simulation yet to determine, and here's what our simulation is going to do. Our simulation is going to help us determine, could this 2.3 difference have been a coincidence? What's the likelihood that this was just a coincidence, that we just luckily put the 20 seeds that were already better to begin with? We would have had no way of knowing that. But what if they were already better to begin with and we happened to put them in the synthetic category by chance? There is a chance that could have happened, right? Because even if we plant all 40 seeds under the same condition, they're not all going to be the same height, are they? Right? So what happens if we already took the better plants and happened to coincidentally put the majority of them in the synthetic? So we have to decide if this 2.3 difference is significant enough, and that's where our simulation is going to come in. So we go to the computer. There's one more simulation link on my webpage that is this mean comp, which is mean comparison, like average comparison. I'm going to jump to my webpage. And mean comparison simulator is right there. Here's the thing about this simulator. A little bit annoying. You have to actually enter the data.
It says mean comps.
It is mean comps, and this is it. This is it. I know this one says DSM Sim, but this is it. Because DSM Sim is now difference of sample means simulator. It used to be called the mean comp, so it's the same thing. You have to actually enter your sample. So you might not want to do this on your phone. Okay? If I do 6, 8, I'm entering 10, 12, 12, 12. I'm entering group 1. Okay, and then I'm going to hit add. So you have to hit add so it processes those. And then you're going to enter your second one. Tell me if I make a mistake because I'm trying to do this fast and I'm not. I'm not looking at the screen. Oh, it looks like that. I don't know if they have the same amount, but add. Okay, so that's added. Number of simulations, it says do 100. Okay, and decimal accuracy 3. Here's what's about to happen. Before I hit run simulation, let me explain what's going to happen. We are taking these 40 seeds. Given that they've already been treated, and we already know which ones ended up growing how much, we're throwing all 40 seeds back into the same pot. And in the first simulation, we're just reassigning the groups. And we're reassigning the groups, calculating the average growth, and the difference between the two groups, and seeing what that is. And then we're throwing all the seeds back in. And then we're remixing up the 40 seeds and reassigning. Okay? And so we're going to do that 100 different times. And we're calculating 100 different averages and the difference between those averages. Does that make sense? Okay, so every time we run a simulation, we're calculating the average of this group, the average of this group, and what's the difference between them. Okay? And I'm going to get a list of 100. Now, our average difference was what? 2.3, okay? So we're going to run a simulation. And we've got a whole bunch of numbers. Now, one thing I will also say about this is it's not organized smallest to greatest. The negatives are actually, this is the smallest negative, and then the negatives continue to increase. And the largest difference we ever get is -4. Now, these differences, by the way, are all coincidental. We know that for sure, because we put all the 40 seeds back in after the treatment had already been issued, and then we're placing them out into 20 groups randomly. So the absolute lowest was -4, and the absolute highest was +3. So if I scroll down, here's what you're going to see. There's the 100 difference, 100 results, the 100 differences of sample means. There's 100 little rectangles there, okay? This says to create a histogram, which I don't think you'd ever have to do on your own, so we're not going to draw this histogram necessarily. But what we need to do is figure out where our 2.3 falls on that list. Okay? Our 2.3 is 2.279. Okay, so our 2.3 is right in here somewhere. So this one's 2.279, this one's a little over 2.3. So out of the 100 simulations, how many coincidentally were greater than 2.3? If I count, there's 1, 2, 3, 4, 5, 6. Agreed? 6 out of my 100 simulations were coincidentally greater than 2.3. Is that a good percentage? I'm going to say 6 out of 100 were coincidentally greater than or equal to 2.3. So 6%. So there's a 6% chance that this 2.3 was coincidental. Okay? So the better thing that we can gather from this is that we are 94% sure that the difference in heights was due to the treatment. I guess I just covered D. So what I just wrote there kind of covers C and D. That percentage can change to your confidence. I am 94% confident that synthetic nutrients will lead to bigger plants. Okay, because that 2.3 difference would be pretty coincidental if it was really due to the fact that, oh, you just so happen to put the better seeds in the synthetic group. Do we follow? Does that make sense? Any questions? No. Okay. All right, so that's just the one big example for an experiment in simulations that we're doing for today. Okay, and you can see how it's different than some of the simulations we've done already, but you can also draw some comparisons as far as always searching for the number that is beyond what we actually found, kind of thing. So flip back to the front. Some of these questions I'm going to throw out. I took another look at them and don't love them. But because this was just one example today, I thought I was convinced we'd have a little time. I'm definitely omitting number 1. I don't think that that's something we need to talk about and confuse people with. But in number 2, explain the difference between the sample mean and the mean of the sampling distribution. Okay? Let's go to sample mean first. Okay, this is going to be kind of more in tune with what we did, not today, but 2 days ago. When you take a sample and you calculate the mean, that's your sample mean. Okay? The sample mean is the average of just one sample that was randomly taken. So you just take one sample to get a sample mean. The mean of the sampling distribution, this would be the average of all of the average. So you take multiple samples. We take a sample, we come up with that sample's average. We take a second sample, we come up with that sample's average. We take a third sample, we come up with that sample's average. And then when we're all done, we take the average of the averages. Okay? So this is the average of the averages of several samples. Like, that's the mean of the means kind of thing that we did. And 100% I'm on board with that's confusing. To say that too quickly, if I just say, oh, the mean of the means, or the average of the averages, that's confusing. I always like to slow it down and kind of paint that picture. You took a sample and you got that sample's average. That would be a single sample mean. But if you do it with multiple samples and you get a bunch of sample means, now when you average together all of those averages, that gives you the mean of your sampling distribution. Capiche? That's what we did yesterday. Okay? And the average of the averages, so I will say this, the average of multiple averages is essentially equal to the population average. Remember, that symbol means population average. So, again, if I want the average number of hours that people spend watching TV, there is no way that I'm ever going to be able to survey everybody that lives in the U.S. It's just not going to happen. It's not practical that I would ever be able to truly get the population's average. But what I can do is I can sample 50 people randomly, and then I can get that average, and then I can sample 50 more people randomly, and I can get that average, and I can sample 50 more people randomly and get that average, and I can take 100 different samples and then take those 100 averages and average those averages. And that will 99% of the time be spot on to what the population average would have been. Okay? All right, number 3. Suppose you are interested in knowing how many text messages 11th graders send daily. Well, that would be you guys. If we wanted to know at Hamburg High School, how many text messages do 11th graders send daily? There's only one exact way to do this. What would that be? Ask everyone. Not just ask everyone, because do you know how many you spend on average, or how many text messages you... We'd probably have to take their cell phone bills and take their monthly average, right? And say, okay, Kaylee, you sent 1,000 this month, and Cole, you sent 922 this month. Okay? Oh, it's not in a month, it's daily. So on average, Cole, you send 120 a day. And on average, Kaylee, you send 132 a day. So the only way to do this would be to get every 11th grader's cell phone bill and figure that out. But no one's going to do that. So describe the steps that you could take to estimate the average number of text messages per day sent by all 11th graders at school. What could we do there? Take a sample of 50, okay, and ask those 50 people, how many do you send per day, how many you send per day, and then average all those together. Okay, what happens, Kaylee, though, if in that one sample of 50 people, you happen to pick a lot of those girls that are never off their phone? You happen to pick, just by chance, your sampling variability would come into play, could come into play here. If you only take one sample of 50, you may get unlucky. You may pick the people that are constantly on their phone by chance. And it would be a coincidence, but it could be, and it would be unlucky, but it could happen. Or you might coincidentally go the other way and pick a few people that don't even own a cell phone, and they have 0. So that throws it off. So taking one sample is not a good generalization of the entire population. you would take a sample of 50 and record that average. But just in case there was sampling variability, you would put those 50 people back and you would pick 50 new people. And some of them might get repeated again. And you would come up with that average. And maybe do this 4 or 5 times. And then average all those averages. And now you're cutting down on that unlucky possibility. Does that make sense? Okay? So I would say you would, and again, always use the word random. Say randomly sample. It doesn't even have to be 50. You could, 30 is the minimum you want to go, so I'm going to say 30. Randomly sample 30 juniors and average their daily text. Then repeat 10 times. And then at the very end, average the averages. That's your best way. Does this make sense? Unfortunately, a lot of the stats questions require you to write sentences. So you have to be able to explain this stuff. You have to know how important the word random is. You have to know how to just express yourself and make sense. Because I find with your explanations that that's the biggest thing. Is half the time, and I'm not even, that even might be generous, 70% of the time, your sentences don't even make any sense. And that's tough. Because I can't sit there and be like, but I'm pretty sure I know what they're trying to say. Wink, wink, but they're not saying it. I can't do that on the Regents. Okay, so we have to be sure we are, take our time and slowly and clearly explain. Okay? Last example. We have 62 random samples. Okay, so it's like we did this. We sampled 10 kids 62 different times. Okay? So we grabbed our first 10 kids, averaged all of them, and it came out to be 65 tests per day, or texts per day. And then we threw all those kids back and we took another sample of 10 kids and we averaged their number of text messages sent per day, 68, and so on. Draw a dot plot. You're not going to draw a dot plot. I did it for you. Okay? And the lowest was 65, the highest was 106, and then I just kind of, you know, if multiple people were at 95, which it looks like they were, I just kind of stacked them up. So these are the 62 different dots, okay? Based on your dot plot, would you be surprised if the actual mean number of text messages sent per day for all 11th graders in the school was 91.7? Look where 91.7 falls. It's right around here. Would you be surprised if that was the population average? No, you shouldn't be. Why not, do you think, Scott?
It's somewhat in the middle of all.
Perfect. That's all you need to say. Because it's somewhat in the middle. Or because it's, what did I write? I put no. Because my samples mean are, what did I write? My samples mean are, yes, heavily. Thank you. Are heavily distributed around 91.7. 91.7 is somewhat in the middle. And all these samples are pretty normally distributed around 91.7. I put in quotations something also like the 91.7 is really in the bulk of the data. But if anyone suggested a number out here on the outskirts, we all know by our standard deviation and our our normal curve that if you're on the outskirts, there's a very low percentage chance that that's going to happen. How many homework assignments do you have this weekend? 2.
Hello.
1 spiral and 1, that's on this simulated stuff. So when you have both, you may go. That first sheet is that, Riley's got this started for me. That's for you. Thank you. Have a great weekend. Did you get an extra? No, Cole's gonna get one chance. Cole, you wanted to do the homework twice, is that what you're saying? I have an extra copy. All right, goodbye. Oh, you know what? Can I run something by you?